This is the Unit 2 practice exam for Math 1050. Question 1 is from section 3.2 where we're graphing polynomial functions. This one is already in factored form. And we want to have it in factored form so that we can find the zeros. That's where I'm going to start. Finding zeros. And then I want to find the y-intercept. And then I want to consider the end behavior. So those are the three steps that were instructed on graphing polynomials. So first, the zeros. Like I said, those come right from the factors. And in addition to stating the zeros, it's also important to state whether or not they bounce off of the x-axis or whether they cross through it, and that has to do with the multiplicity. For example, this first factor, x plus 1, is going to give us a 0 of x equals -1. But because of the multiplicity here of 2, and even multiplicity, if you'll remember, even multiplicity means that it bounces off the x-axis. So I'm going to state that it bounces. Now this factor here, x minus 3, will give us a 0 of x equals +3. And because the multiplicity is 1, I'm going to say that at that 0, it crosses through. Okay, the y-intercept, remember we find the y-intercept of any function by letting x equal 0, or substituting a 0 for all the x's. So plug in a 0 here, 0 plus 1 is 1, 1 squared is 1, and then 0 minus 3 is -3, 1 multiplied by -3 is -3, so the y-intercept is the point 0, comma, -3. So we have our x-intercept there. Now the end behavior is determined by the degree, if you remember, and the degree of a polynomial in factored form, we need to consider how many factors there are. X plus 1 squared means there's 2 of these factors, and then another one here, so there's 3 total factors. This would be a degree 3 polynomial. And a degree 3 polynomial, so this is degree 3, and the leading coefficient here in front of the polynomial is positive 1, which means the right side is up to infinity, the left side is down to -infinity. So right side up, left side down. So what we need to figure out now is how we're going to connect this left side to the right side. So I'm going to start on the left side and move up. Once we get to this x-intercept, or this 0, remember we already stated that it bounces, so it's going to bounce right off and head back down right to this y-intercept. And now we need to determine how far down will it go before it turns back up and head towards this x-intercept. So remember, if there's a large enough gap between zeros, you need to plug in an integer value. So I'm going to plug in a 1, you could plug in a 2, either one. So I'm going to plug in x equals 1 for all of these values, for all the x values. 1 plus 1 is 2, 2 squared is 4, so we get a 4 right here. And then 1 subtract 3 is -2. 4 multiplied by -2 is -8. So when I plug in a 1, I get -8. Right about down there. So it does go down a little bit farther before it comes back up. Now with that x-intercept, we just got to check. At x equals 3, it crosses through and connects back up with that side. Okay, question 2, this is from section 3.1. We have a quadratic function here. Now it's in general form, and the task is to write it in standard form or vertex form to find the minimum or maximum value and sketch the graph. So the process we're going to use, remember, is called complete the square. So what I'm going to do first is move this plus 11. I'm going to subtract it over here. So subtract 11 on both sides. And then I'm also going to factor out the 2 from these two terms. I'm not going to factor it out from the constant term because remember we moved it over here, so I'm going to factor out a 2 from the 2x squared and the negative 12x, and only the 2, not a 2x, just the coefficient of 2, which will leave me x squared minus 6x, and I'm going to close the parenthesis. Remember, this is how we showed it during the lesson for 3.1. I'm going to close the parenthesis far enough to the right to include a spot where I can add a new number. So I need to add a value here that will complete the square. So the value that we'll add there, if you recall the formula, we have b divided by 2 raised to the second power, where this is b right here. So half of b, or half of 6, negative 6 is negative 3. Negative 3 squared is positive 9. So I'm going to be adding a 9. And this point now is where the most common mistake occurs on a problem like this. What we've done is added something to the right side of the equation, and in order to keep things balanced, we have to add the exact same value to the left side. Now the value that was added appears to be a 9, but recall, if this 2 were distributed back into the parenthesis, it would be 2 times 9, which is 18. So we really added 18 to that right side. So we need to add 18 to the left side to keep the equation balanced. Now, this now forms what we called a perfect square trinomial. X squared minus 6x plus 9 factors into x minus 3 multiplied by x minus 3. So we can rewrite this as x minus 3 to the second power and subtract the 7 back over to get the function now in standard form or vertex form. So the vertex, if we consider the transformations that have occurred, x minus 3 inside the function means the graph moves to the right 3 units and down 7 units. So the vertex is at the point 3 comma negative 7. And because our leading coefficient is positive, this means the parabola is going to open upward, which makes our vertex a minimum value. So the vertex is down here at 3 comma negative 7. And we need to graph. So remember what has been required for these quadratic function graphs. We need 3 points. So the vertex here counts as one of the points. So we just need 2 others. So what I'm going to do is plug in an x value that's near where the vertex is. So the vertex occurs when x equals 3. So I'm going to plug in x equals 2 into the function and see what the value is there. So if I plug in a 2 for x, 2 minus 3 is negative 1. Negative 1 squared is 1. 1 times 2 is 2. 2 subtract 7 is negative 5. So when I plug in a 2, I got negative 5. Which is right here. Now, parabolas are symmetric, so that point can be reflected across on the other side, and that will give us our parabola. Okay, question 3, finding zeros. This is a big part of chapter 3. It covered section 3.4 and 3.5. So to find the zeros, first step is to make a list of possible rational zeros. Remember, that's our P and Q. So the factors for P are going to come from the factors of the constant, 34. So that's plus or minus 1, plus or minus 2, plus or minus 17, and plus or minus 34. Now we need to choose, we need Q. So Q is the leading coefficient. In this case, Q is equal to 1, and so if you divided all of these values by 1, it wouldn't change any of them. So this becomes our P divided by Q list. Okay. So we need to test values now and see if we get a remainder of 0 in synthetic division to determine if we have found a 0. So we could start with 1, for example. And always wise to check your polynomial. We have an x to the third, so that means we need to have an x squared term, an x term, and a constant term. If any of those terms are missing, we'd have to have a 0 in its place when we do synthetic division. So we're just going to use the coefficients. And then go through the synthetic division algorithm. So it doesn't look like x equals 1 is a 0. Try negative 1. Okay, didn't look like that worked. So we could try 2. Okay, it looks like we found it. X equals 2. So what we have found is that x equals 2 is a 0. And we have also found then that the factor x minus 2 is a factor of the polynomial. These coefficients here give us the coefficients of the reduced polynomial x squared minus 6x plus 17. So we haven't fully factored p of x. If it's a third degree polynomial, we should have 3 factors. We only have 2. So what that means is this needs to factor down into 2 more factors because it's a degree 2. It's going to have a quadratic. It's a quadratic, so we're going to have 2 more factors. Now, sometimes this quadratic factors easily, sometimes it does not, and we have to use the quadratic formula. In this case, we need to use the quadratic formula to find the remaining 2 zeros. So the opposite of b is positive 6. And then b squared would be negative 6 to the second power, which is 36, minus 4 times a times c divided by 2 times a. So we need 36 minus 4 times 1 times 17. Now 4 times 17 is 68. So this is 36 minus 68. So that's going to give us negative 32 right there. Now, the square root of negative 32 doesn't exist. We have to use the imaginary number now. So that negative sign will be replaced with an I. You can either put the I in front or behind it. I usually put it in front. And then we need to simplify the square root of 32. So I'm going to do that up here. The square root of 32. The way I like to do this is when I'm simplifying square roots, I think of the highest perfect square that's a factor of 32. Now when I say perfect square values, that's 1, 4, 9, 16, 25, 36. Those are all perfect squares. So the largest perfect square that's a factor of 32 is 16. So I'm going to change 32 into 16 multiplied by 2. And then one of the properties of square roots is if you're finding the square root of a product, then that's the same as individual square roots of each factor of that product. So instead of the square root of 16 times 2, it's the square root of 16 multiplied by the square root of 2. The square root of 16 is 4. So that turns into 4 times the square root of 2. So I'm going to change the square root of 32 into 4 square root of 2, and the 4 and the I are going to multiply to make 4i. Now you notice I have a value here, 6 plus or minus 4 divided by 2. So we do need to simplify one step further. From the numerator, both the 6 and the 4 have a factor of 2 in common. So if I factor out that 2, that leaves me with 3 plus or minus 2i square roots of 2 divided by 2. Again, what I've done here from the 6 and the 4, I factored out a 2, leaving the 3 plus or minus 2i. And the reason I did that is now I can factor out these two 2's. I can cancel them out. So the final version of that is 3 plus or minus 2i square roots of 2. So those now would be all of the zeros found. So I'm going to make a list here. The first one we found is right here, x equals 2. And the other two that we found were right here, 3 plus or minus 2i square roots of 2. All right, question 4. This one came from section 3.5. We need to find the equation of a polynomial that's degree 3, so it needs to be some kind of p of x equals x to the third, or 2x to the third or something. It needs to have x to the third as its highest exponent. And the fact that it's degree 3 means we need to have 3 zeros. So they've given us 2. So what we need to be able to remember is this kind of a 0, these complex zeros, remember, always come in pairs. So if x equals 2 plus 2i is a 0, then we assume that x equals 2 minus 2i is another 0. And then we have x equals 3. So those are our 3 zeros that we're going to use to form the 3 factors we need to multiply together to form the polynomial. So I'm going to do this one first. So x equals 3. If I subtract 3 on both sides, I get x minus 3 is equal to 0. Once you have the equation equal to 0, then that side over there becomes one of your factors. So x minus 3 is a factor. Now here, if I subtract 2 and subtract 2i, I get x minus 2i is equal to 0, so that's another factor. And then here, if I subtract 2 and add 2i, so I have x minus 2 plus 2i is equal to 0, so now that becomes the third and final factor. So this would be p of x in factored form. Now we need to multiply these together to get it in general form. So I'm going to multiply the 2 factors together first that contain the imaginary parts. So just use the distributive property to multiply there. So the x times x is x squared, and then x multiplied by negative 2 is negative 2x, and then x multiplied by 2i is positive 2ix. Now we multiply the negative 2 and distribute it into that parenthesis. So negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4, and negative 2 times 2i is negative 4i. Now we're going to multiply the negative 2i and distribute it. So negative 2i times x is negative 2ix. Negative 2i times negative 2 is positive 4i. And then negative 2i times positive 2i is negative 4i squared. So what should happen now is any term that contains I should cancel out with an opposite term. So 2i, negative 2ix, we had the negative 4i, positive 4i, and then this term right here, remember I squared is equal to negative 1. So what this is really negative 4 multiplied by negative 1, which is positive 4. Now we can combine this positive 4 with that positive 4, making plus 8. Negative 2x makes negative 4x. And then we can multiply with this other factor, x minus 3. Using the distributive property again, we're going to distribute there to get x to the third minus 4x squared plus 8x, and then if we distribute the negative 3, we would get negative 3x squared plus 12x minus 24. So combining like terms, we would have x to the third minus 7x squared plus 20x minus 24. Question 5 here comes from section 3.3. So the ultimate task here is to find the value of this polynomial when x is equal to 3. Now normally you would just plug in 3 for all the x's and evaluate it, but it says specifically here use synthetic division and the remainder theorem. This was part of the instruction in section 3.3. So what we need to do is synthetically divide at the value of 3, and whatever our remainder is, that's going to be the value of the function when x is equal to 3. And let's see, 3 times 20, that's 87. 87 plus 9 is 96. So P of 3 is equal to 96. That you would need to show that statement here in order to receive full credit, because the end result of this problem is not just to use synthetic division and remainder theorem, it's to use that to show the value of the function when x is equal to 3. So you would need to show that statement right there. Okay, question 6 is kind of a combination of a few sections. So finding the zeros and writing it in factored form is from section 3.4, 3.5, but then sketching the graph of the polynomial is from section 3.2. So for part A, what we would need to do first is have our list of P and Q values to test. So the factors of P, remember, or the values for P are the factors of the constant. So for A, we have plus or minus 1, 2, 4, and 8. And then Q, again here, Q is just equal to 1. So dividing all of these values by 1 is not going to change any of those values. So that is our P divided by Q list. So now we need to find a few that work. So I'm going to start with 1. And we have one that works. So what we have, though, is x minus 1 is one of the factors. The remaining factor that is going to be formed from these coefficients is a third degree polynomial. And we cannot use factoring or quadratic formula on a third degree polynomial, so we're going to need to factor this. We're going to need to use synthetic division one more time on this polynomial here from the list of possible rational zeros. So I'm going to try -1. And again, I'm going to synthetically divide on this smaller polynomial. And it doesn't look like -1 works. So we can try +2. Okay, it looks like +2 works. So we have another factor. So we first had x minus 1 from that first step, and now we have x minus 2, and then a smaller polynomial is formed from these polynomials, or from those coefficients, which is a quadratic factor. And then that can factor into x plus 2 times x plus 2. So So this is part B, fully factored form. Part A, we would need to list all of the zeros. So we had x equals 1, x equals 2, and then these two factors are both going to give us the same 0 of x equals negative 2, and that has multiplicity 2. And remember from the problem we did right at the beginning of this, even multiplicity means that the graph is going to bounce. So I'm just going to say it bounces right there for when we get to part C, which is where we graph this. So those are the zeros. This is the polynomial in factored form. So now for part C, we need the zeros on there. And then we need the y-intercept. Remember, the y-intercept occurs when x is equal to 0. So if you plug in a 0 for all of the x's here in general form or for all the x's here in factored form, you would get 0, 8 as your y-intercept. And then the degree is degree 4. So remember, with even degrees, both sides of the graph, the left side and the right side, are going in the same direction. And since we have a positive 1 as the leading coefficient, the graph is pointing upward. So the left side is pointing up and the right side is pointing up. So we need to figure out how to connect this left side to the right side. So as we approach this first x-intercept of negative 2, we already decided, because of right here and because it has multiplicity that's even, it bounces. So it's going to bounce off the x-axis and come right back up. Now we have this gap right here between negative 2 and 0. And whenever you have that integer value gap, remember you need to plug in negative 1, in this case negative 1. So I'm going to plug in negative 1 for all of the x's here and see what the value of the function is. So negative 1 minus 1, that's negative 2. Negative 1 minus 2 is negative 3. Negative 1 plus 2 is 1 and 1. And all of those multiply to get 6. So negative 1, 6 is a point on the graph. So it goes up through 6 up to our y-intercept of 0, 8, and then it comes back down. Now at x equals 1, which came from this factor right here, the multiplicity is odd, so it crosses through. And at x equals 2, the multiplicity is odd because it has an exponent of 1, so it crosses through there as well. So it crosses through at x equals 1. Now between 1 and 2, remember there are no integer values to plug in. So I don't expect you to plug in decimal values, so you just need to turn it up at some point and connect it to the other side of the graph. Question 7 comes from section 3.6, graphing rational functions. Now the way that this was instructed, kind of broken down into 3 parts. Part 1 is to find the intercepts. So I'm going to find X-intercept and Y-intercept first. And I'm actually going to start with the Y-intercept. Sometimes is the easier of them to find. Remember, the y-intercept occurs when x is equal to 0. So if all of the x's here are equal to 0, you'd be left with negative 6 divided by negative 8, which is 0.75. So the y-intercept is 0, 0.75. Now the x-intercept, or intercepts, there could be more than one. Those occur when y is equal to 0. In this case, r of x would be 0. And in order to solve this equation, remember we're going to want to get rid of this fraction. So if I multiply both sides of this equation here by the denominator, that's going to clear the fraction here. But then if I multiply over here by the denominator, I'm still going to get 0, because 0 multiplied by anything is 0. So what would we be solving then is just this equation in the numerator, 0 equals x squared minus x minus 6. You can factor that into x minus 3 times x plus 2, so that we have solutions of x equals positive 3 and -2. So those would be our two x-intercepts, 3, 0, and -2, 0. So I'm going to write that in factor form, x plus 2, x minus 3. Now we're also going to want to factor the denominator into x plus 4 and x minus 2, because that brings us to step 2 now. Step 2, after we've done the intercepts, we want to find the asymptotes. So the vertical asymptote, in this case there's going to be 2 of them. Those, remember, come from the domain restrictions. So wherever the denominator would be 0, that's where you're going to place a vertical asymptote. So the denominator would equal 0 at x equals -4 and at x equals +2. So x equals -4 and x equals +2. Now, the horizontal asymptote, remember, that is found by comparing the degree of the numerator to the degree of the denominator. So the numerator is degree 2, the denominator is degree 2. So you need to recall, whenever they are the same degree, you divide the leading coefficients. So the leading coefficient of both the numerator and the denominator is 1, and 1 divided by 1 is 1. So the horizontal asymptote is y equals 1. So there's step 2. Step 1, finding the intercepts. Step 2, finding the vertical and horizontal asymptote. Now step 3 is just putting the graph together. So because we have 2 vertical asymptotes, that's going to separate the graph really into 3 parts. Here on the right side of x equals 2, in between the 2 asymptotes here, and then on the left side of x equals -4. So I'm going to start over here on the right side of this vertical line, x equals 2. Now, the graph is either going to be contained in this top right portion or this bottom right portion here. And the fact that we already have a point located right here tells us where it's going to be. Because that's always the suggestion I make, is if you're trying to decide whether the graph is going to be above or below that horizontal asymptote, plot a point. And we already have one plotted here. It's our x-intercept. So that tells us that the graph will go through that x-intercept like that. I'm going to skip over the middle part for a second and come over here to the right. We need to do, or to the left, we need to make the same determination. Either the graph is going to be up here, the top portion, or down here in the bottom portion. Now, if we're saying it's going to be in this bottom portion, eventually somewhere it would have to cross through the x-axis, and there is not an x-intercept anywhere over here. So the graph would not be able to cross through the x-axis like that, which means it's going to be contained in this top portion. Now, if you didn't follow that reasoning, or if you're worried about making that kind of determination, you can always plot points. So if you plotted an x value of -5, for example, if you plug that into the function, -5 plus 2 is -3, -5 minus 3 is -8. So -3 times -8 is 24. And then in the denominator, if you plug in a -5 plus 4, that's -1. -5 minus 2 is -7. So -1 multiplied by -7 is +7. And then 24 divided by 7 is 3 point something. So at -5, we're all the way up here at, in between 3 and 4. So that means that piece of the graph looks something like that. Now, in between the 2 vertical asymptotes, we already have 2 points located, the y-intercept and this other x-intercept. and those points are going to be connected. And then the graph always crosses through a y-axis, never bounces off a y-axis. So right here, we've crossed through, and the graph either needs to continue to head up to positive infinity, or the graph will need to head down to negative infinity. It never just stops when it reaches a vertical asymptote. It either approaches infinity or negative infinity. Now, in order for this graph to approach, at this point right here, to approach negative infinity, there would have to be an x-intercept somewhere right here to allow it to cross through the x-axis. There is not an x-intercept right here, which means the graph has to stay above the x-axis and continue up to infinity, like that. Now here at this point, we need to make a similar determination. Is it going to come down here to negative infinity, or is it going to come back up and approach positive infinity? And one thing we could do is just plot another point of x equals -3. So plug in -3 plus 2, that's -1. -3 minus 3 is -6. -1 times -6 is +6. Here, -3 plus 4 is +1. -3 minus 2 is -5. 1 multiplied by -5 is -5. So 6 divided by -5 is -1 point something. So right about right there, which means the graph would head down to negative infinity. Okay, so there we have the graph. It asks for domain. So the domain is going to be negative infinity to -4. You see how here at -4 it breaks, and then -4 to 2, and then 2 to infinity. Okay. Question number 8 is also from section 3.6. So we'll do the same technique. We need to find intercepts first, so X-intercepts and Y-intercepts. So starting with the Y-intercept, when we let x equal 0, we're going to have all of these variables disappear and have -2 divided by -8, which is 1/4. So 0, 1/4. Now the x-intercept occurs when y is equal to 0, in this case r of x, and remember that will only happen when the numerator is equal to 0, so x minus 2 equals 0 only when x is equal to 2. So we have 2, 0 as our x-intercept. Now we find vertical and horizontal asymptote. So vertical asymptote, I'm going to go ahead and factor the denominator into x minus 4, x plus 2. So that tells us when we have an x value of 4 or an x value of -2, we would have the denominator equal to 0, and that's exactly where we want to place those vertical asymptotes. Those are the domain restrictions. X cannot be 4 and x cannot be -2. That's precisely what the vertical asymptotes are there for. So at 4 and at -2. Now the horizontal asymptote, remember, comes from comparing the degree of the numerator to the denominator. The numerator we can see is degree 1 right here, and then the denominator is degree 2. So this is where you really need to have this studied and look over it enough times to remember that when the numerator has a smaller degree than the denominator, then the horizontal asymptote is the line y equals 0. Okay. So we're to the point now where we can start piecing this graph together. So like on the last problem, I'm going to start here on the right side. So either the graph will be up here in the top right, or it'll be down here in the bottom right. Now there aren't any values here that have already been plotted, so we need to plot a point that's on the right side of this vertical asymptote x equals 4. So I'm going to choose x equals 5. and plot that point. In the numerator, 5 minus 2, that's going to be 3. In the denominator, 5 minus 4 is 1, 5 plus 2 is 7, 1 times 7 is 7, 3 sevenths, that's just about a half. So just the location of that one single point is enough to know that that graph, or that piece of the graph rather, is up there above the horizontal asymptote. Now I'm going to go over here to the left and do the same thing. I'm going to plot a point to see whether the graph is up here or down here. So I'm going to plot when x equals -3. So if I plug in -3 for x in the numerator, that's going to be -3 minus 2, which is -5. In the denominator, -3 minus 4 is -7. -3 plus 2 is -1. -7 times -1 is +7. So -5 sevenths is just slightly over -1/2, right about there. So the location of that point is enough to know that that piece of the graph looks something like that. Now in the middle, the x-intercept and the y-intercept have to be connected because there's no vertical asymptote to separate them. And it does, remember, always cross through the y-axis. And it's going to continue upward toward positive infinity. And the reason is it cannot turn down towards -infinity. Otherwise, it would have to cross through the x-axis, and there is not an x-intercept right here that will allow it to do that. Now, right over here, determine what the graph does. Does it bounce off and come up like that? Does it cross through and go down like that? We can plot a point right here when x equals 3 to figure that out. So if we plug in a 3 for x, in the numerator, 3 minus 2 is 1. In the denominator, we're going to get 3 minus 4, that's -1. 3 plus 2 is 5. -1 times 5 is -5, so it's -1/5, which is right about there. So it looks like it continues downward towards -infinity. Like that. Okay, now the domain, we have -infinity all the way to -2, and then -2 to 4, and then 4 to infinity. And those are the same domain restrictions that we found at the very beginning of the problem when we factored the denominator. X cannot be 4, so we exclude 4 right here, and x cannot be -2, so we exclude -2 right there. Question 9 is from section 3.1. We have a description here that the initial velocity is 72 feet per second. That's reflected in the equation here. -16 is just the effect of gravity. So the height of the ball at any time t is modeled by this equation. How long does it take the ball to reach its maximum height? We talked about this word maximum. In this case, this is a parabola that's facing upside down because it's -16 coefficient. So the maximum point of a parabola that's facing upside down is the vertex. So when it says find the maximum height, really what they're asking us to do is find the vertex. If we were to consider the graph of this, it would look something like this, where the horizontal axis is time and the vertical axis is the height. So we're trying to figure out at what time value it reaches its vertex. So I'm just going to use the vertex formula. Instead of x equals, we're going to use t equals the opposite of b divided by 2a, where the opposite of b is -72, and then 2 times a would be 2 times -16. So the negatives will cancel, and we have 72 divided by 32, and that will simplify to 9/4. And since this is a value of time, and the unit of measure right here is in feet per second, so the time value is going to be in seconds, so that's 9/4 rather, of a second. Now what is the maximum height? What we found here is the x value, or the t value of the vertex, so now we need to find the height value just by plugging 9/4 into the equation. So the height at 9/4 of a second is equal to the value of the function when we replace t with 9/4. So 9/4 squared is 81/16 multiplied by -16. So the 16s will cancel, leaving -81. And then here, 4 goes into 72 18 times, and then 18 times 9 is 162, and then add those together to get 81 feet. Now, how long does it take for the ball to hit the ground? If we think about this equation here, and the reason I have the graph starting at the origin is because the height is the vertical axis and the ball starts on the ground. So it starts at ground level, comes up to its maximum height at 9/4 of a second, and then comes back down to ground level. Now, if you want to think about the logics of this problem, if it takes 9/4 of a second to come up to here, the parabola is symmetric. It's going to take another 9/4 of a second to come back down. So 9/4 plus 9/4 is 9/2 of a second. That's one way you can answer this question. The other way is to use the equation. If the height is represented by this formula, when the ball hits the ground, the height is 0. So you could replace h of t with 0 and solve the equation for t. Now, both of these have t as a common factor, and they also have 8. So I'm going to factor out a -8t, and that would leave 2t minus 9. So that gives us two values of time, t equals 0 and t equals 9/2. Well, obviously, at time t equals 0, the ball's on the ground because it starts there. And then at time t equals 9/2, way over here, it's on the ground again. So the answer, how long does it take for the ball to hit the ground, is 9/2 of a second. Okay, number 10, perform polynomial long division. This was from section 3.3. So the numerator goes inside the long division bar. And if there are any missing terms, remember those need to be represented with a 0 to hold the place of those missing terms. The denominator goes out here. And now we're just looking for the first term into the first term. So how many times does 2x squared go into 10x cubed? Or what value would I need to put here so that when I multiply it by 2x squared, I get 10x cubed? Because remember, you want these first terms to cancel. So if I multiply 2x squared by 5x, then 5x times 2x squared is 10x cubed. So 5x would be the term that goes up there, and then multiply the 5x to this whole polynomial, and that would give us 10x cubed minus 5x squared plus 20x. Now remember, you need to subtract that entire expression now from the one above it, so the 10x cubes cancel. Negative times a negative is a positive, so that's 6x squared, and then this is negative 20x from 18x, which is negative 2x. Now drop down the 2 and continue on. How many times now does 2x squared go into 6x squared? Or what value could I put up here so that when I multiply it by 2x squared, I get 6x squared? So if I take 2x squared and multiply it with a plus 3, that would match this 6x squared, which is what I want to have happen so I can cancel it. So now multiply the plus 3 to this entire polynomial, and you're going to get 6x squared minus 3x plus 12. And now this is going to be subtracted. So the first terms cancel, which is what we want. Negative times a negative is a positive. So that's positive 3x minus 2x, which is 1x. And this is a negative 12 from positive 2, which is negative 10. Now, this becomes the remainder. And what we talked about is once the whatever is left over here has a smaller degree than this, then that becomes your remainder. So we have the quotient here plus the remainder divided by the divisor.